All right, the last thing we talked about on Friday was this Maxwell-Boltzmann distribution, and just the idea that in any sample of stuff, you're going to have some particles moving really quickly, some particles moving more slowly. The average is somewhere in the middle, and there's going to be this distribution. An important feature of the distribution is over on the right side, the fact that the distribution has a tail over on the right side, where it's sort of an asymptote approaching zero, but it doesn't actually go to zero. That's an important fact for us. What that tells us is there's always going to be a few rogue particles that are moving really quickly, even at relatively low temperatures. There's always going to be some particles that are moving really quickly, and so reactions that take a lot of energy. When we study reactions later in the year, reactions that take a lot of energy, there's always going to be a few particles there that can do those reactions. So they'll still occur just very slowly at low temperature. It's just when you raise the temperature, you give more and more particles enough energy. There's more and more particles in that tail over on the right, and then they have enough energy to do whatever you want. The other thing I'd point out is as you raise the temperature, what happens is this spread gets wider, right? It moves to the right and gets a lot wider. The height gets lower, so there's more distribution of speed at higher temperatures. At lower temperatures, things are kind of bunched up over here to the left. You see the blue curve. Things are more bunched up over to the left at lower speeds. As you raise the temperature, it gets really spread out, so you have a much wider spread of molecular speed. And so I want you to picture in your mind, when you think about atoms moving around, molecules moving around, picture in your mind that distribution. Some are moving quick, some are moving slow. Now in this class, the way that temperature will interact with us, or the way that energy can pass from one thing to another, is going to be through heat transfer. And the one thing you need to know about heat transfer is heat always passes from hot to cold. Pretty intuitive idea. But the idea is heat transfer is when fast-moving particles bump into slower-moving particles and transfer some of their kinetic energy. So when you think about why a hot thing in contact with a cold thing makes the cold thing get hotter, just think there's millions and millions of collisions going on, and in each one of those collisions, a faster-moving particle might transfer some of its energy to a slower-moving particle. And when it does that, it helps make the colder thing get warmer, helps make the warmer thing get colder. All right. So just think of fast-moving particles or faster-moving particles. Bump into slower-moving particles. And transfer a little bit of kinetic energy. And if that happens millions and millions of times, eventually it's going to lead to one set of particles getting cooler, one set of particles getting warmer. The main form of energy transfer that we're going to see in this class is through heat, through faster moving things, bumping into slower moving things, and giving them some kinetic energy. All right. So that's pretty much the end of the energy discussion for now, the introductory energy discussion. We're going to be going on and talking a lot more about energy in every single unit all year. But that's the end of it for now. The last little piece of this introductory lecture is just to say something about quantum mechanics. And all I'm going to say about quantum mechanics is it's really complicated, and you just got to trust it. We'll have a more detailed talk about it later this week, but just know that it's really complicated. But it works really well. Um, over the last 80 years or so, 90 years or so, quantum mechanics has been tested over and over and over and over and over, and it's passed every single test. It's one of the most tested theories ever, and pretty much it passes every test. So it makes really good predictions. We're just going to scratch the surface of it and use it to explain the things we can use it for. So all year when we want to explain stuff, your explanations are usually going to come down to a few things. Coulomb's law, energy transfer, or quantum mechanics. And one of those things is usually going to be the right answer. Coulomb's law, you can have a pretty good understanding of. Energy transfer and potential and kinetic energy, hopefully you'll develop a good understanding of that. Quantum mechanics is the one piece where I'm going to say we're not really going to understand it. We're just going to say, well, that's what the math of quantum mechanics says, and so we go with it. And if you really want to ponder why quantum mechanics works, that's like beyond the level that I can even ponder. It works just because it does. And, you know, if you ever read Scientific American, it's like every month Scientific American practically has an article about quantum mechanics, and they try and explain it in some understandable terms. And I try and read them every month, and I'm like, yeah, this is worthless. I'm sorry, I can't read about quantum mechanics because it just doesn't make any sense. But it's something if you want to ponder, it's really interesting. All right, so that's the end of the introductory lecture. One thing we're going to try and do at the end of lectures is run through the objectives. So the things that Mr. Bennett and I thought were most important for us to know. And then there's AP learning objectives. So this new AP curriculum came out this year, and if you read the introduction to the story of Chem, you can see I talked about the relationship between our course and the AP course, or at least story of Chem and the AP stuff. If you haven't read that, you should probably start reading that packet that I gave you, the front of the lecture notes packet. But they have this set of learning objectives. So we've tried to correlate them with where they fit in the course. And so for each lecture, we'll try and just go through and check off what we think we've taken away. So take a minute to read through those. Check off ones you think you can check off. Like, all right, I understand what that means and I can do it. And make a note of any that you don't feel like you can check off. And we can take questions about them. Yep, there'll be a quiz on the problem set on Wednesday. No. Yeah, so I'll take questions about the problem set in a few minutes. Definitely. I gotta say, let's go through the list top to bottom. All right, so apply law of conservation of mass and energy to solve problems. Questions there? All right, check. Apply Coulomb's law of electrostatic forces to determine the relative strength of strength and direction of forces on charged objects. Questions there? So the question is, does mass play a role in Coulomb's law? It doesn't. Mass plays a role in gravity. So if it's a gravitational situation, then mass plays the same role as charge does for Coulomb's law. So the law of gravity looks a lot like Coulomb's law, except it's mass 1 times mass 2 instead of charge 1 times charge 2. Yep. All right. Describe transformations between kinetic and potential energy. I think we're good there. All right. Check the relative potential energy. Compare the relative potential energy of two different situations involving objects that attract or repel. Questions there? The main principle being, if they attract each other, they have greater potential energy when they're further apart. If they repel each other, they have greater potential energy when they're close together. Use the concept of potential energy to determine if a process is endothermic or exothermic. Oh, I forgot to mention those terms. Let's go back to the heat transfer page. This is why we have the checklist. So I make sure I do the things I need to do. So when we have a process that releases heat to its surroundings, or anything that gives off heat to its surroundings, we call that an exothermic process. And what that means is, if it's releasing heat to its surroundings, that means it's taking some of its potential energy and turning it into kinetic energy. Because when you release heat, essentially, you're giving more kinetic energy to the surroundings. So, in that case, it's turning potential energy into kinetic energy. And any process that absorbs heat from the surroundings will be called endothermic. And for an endothermic process, that's where you're taking kinetic energy from the surroundings and turning it into potential energy. So an example of something that's exothermic would be anything burning. When you burn something, you're taking the potential energy that's contained in that substance, that chemical potential energy, you're releasing it as heat. You're heating up its surroundings. So you're turning potential into kinetic. That's exothermic. So burning would be an example. Something that's endothermic. You boil water. You're putting in heat to make that water go from liquid to a gas. When you make water go from liquid to a gas, you're actually increasing its potential energy. So water evaporating or water boiling would be an example of something endothermic. I knew there was more I wanted to write on that slide, but I forgot. So I'm glad we did that. Right, so questions about endothermic versus exothermic, those terms. All right, we didn't. I didn't lecture about this. I gave you. It's in the handout. A whole several pages of on unit cancellation and some practice problems on unit cancellation. Questions about using unit cancellation to convert units. That's something we can also work on individually if you need help with it. Use and interpret numbers in scientific notation. Again, that's just in sort of the appendices of the story of Chem that you have in the packet. Hopefully you're all familiar with scientific notation. Identify and describe the uses of the most commonly used glassware in the lab. Again, that was just kind of in there. We'll come across it throughout the year. But we just want to give you a little intro. All right, and then there are a couple of learning objectives from the AP curriculum that we thought were relevant. So relate temperature to the motions of particles either via particulate representations, such as drawings of particles with arrows indicating velocities, and or via representations of average kinetic energy and distribution of kinetic energies of the particles, such as the plots of the Maxwell-Boltzmann distribution. You can see the objectives that Mr. Bennett and I wrote are in a little bit simpler language. This is the language of the AP test, or as I like to call it, the Wizard of App. Are there questions about what that means? Yeah, so in the problem set, you had a problem where I gave you different drawings with little particles, with arrows, that kind of thing. That would be particulate representation, such as drawings of particles with arrows indicating velocities, and or representations of average kinetic energy and distribution of kinetic energies. So this other part would be that Maxwell-Boltzmann distribution graph that we talked about. The main idea being you should recognize that in a sample of particles, they're going to be moving in all different directions. Some are going to be moving slowly, some are going to be moving quickly. The average kinetic energy will go up if you increase the temperature. Main idea is there. All right, and then objective 2. Generate explanations or make predictions about the transfer of thermal energy between systems based on their transfer being due to a kinetic energy transfer between systems arising from molecular collisions. I can't even say that without laughing. How unnecessarily complicated can they be? This is basically saying heat gets transferred from hot things to cold things, right? Make predictions about the transfer of thermal energy based on this transfer being due to a kinetic energy transfer between systems arising from molecular collision. It means fast-moving particles bump into slow-moving particles and transfer some of their energy. Yeah. All right. Not all of them are worded like that, but some of them are. If you put it in fancy language, then people are more willing to pay for your advanced placement tests and such. Like, ooh, that sounds impressive. All right. So we'll stop there, and then if there